Okay, can you guys hear me?
Yes.
Okay. If you guys don't mind, maybe one of you can, turn on the camera so that it's a little bit interactive. Thank you. Okay. So, okay, we have seven of you here. So first, I want to ask, how do you guys feel about the homework?
I had a question on 2B regarding how to find the wavelength.
Oh yeah. So for the detailed questions, we can leave it after the class.
Okay.
Yeah. But I'm just like asking, like in general, is it a lot or too difficult? Because this semester is different, right? You guys are learning online, and this homework are the same as previous years when students are learning in person. So I want to know, like in general, do you guys find it too difficult or any thought?
There was a big jump in difficulty from questions 1, 2 to 3.
Okay. Yeah. So later tonight, like after you submit your homework, I would put the solution to your personal folder, and then you will see that this is actually kind of, well, it will be like this throughout the semester. Is that at first you would think, okay, the math is a lot, but then when you really look at the solution, you find it's actually just a few lines if you do it correctly. Okay, so like I would say my math is not bad, but also I don't feel the necessity to test the math of my student, right? Because this is a physics or engineering class; it's not a math class. Yeah. Any other comments or thought? Yeah. So in general, I would say like if you find yourself spending more than 6 hours, then probably there's something you can do to optimize it. For example, take a look at the homework in advance, because we have because the homework is released 2 weeks before the deadline, right? So you actually have 2 office hours you can use. So make sure that you understand the question, otherwise you can waste a lot of time. And the second is probably find a friend or friends to do the homework together. Okay, and yeah, my feedback from previous years is that the homework is challenging but doable. Okay, and you guys are from UVA, right? I heard that you're the best from Virginia, and then Virginia is a relatively large state, so you guys should be challenged in some way. Okay, so now first thing is that there's a math hint in problem 3, question A. The math thing is actually wrong, but either way, if you use that math hint and then you get your answer, you will get all the credit. It's just a stupid mistake I made when I type in the equations. Okay. Now let's come back to the class. In the previous in Tuesday, we already explained. Actually, we already introduced all 6 postulates of quantum mechanics, and all of them are actually based on experiment, right? Based on experiment observations, and then you make a reasonably assumptions of what the quantum mechanics system would be. Okay, and then of course later these postulates were tested again and again with experiment, and then it's with very high confidence to say today that all those postulates, at least to what our existing experiment condition, well, our experiment capability, all those postulates are correct. Okay, so let's just quickly review it. The first postulate is that the system, a quantum system, is fully determined by a wave function, and then the second postulate, I'll add a star here because it's not an independent postulate. It can be derived from postulate 4 to 6. Is that the meaning of the wave function is the probability density, right? The probability of finding the electron between place A and B is the integration from A and B of the amplitude square of your wave function. Right? So this is the probability nature of quantum mechanics. And then the third is that the wave function, is linear. Right? So if you have two possible configuration or two wave functions that satisfy, that are solutions to your system, then their linear combination is also a solution to the system. And then, let's see, P4. And then the fourth to sixth solution postulate regarding the quantum measurement, because from the experiment, what people found is that you can only measure eigenvalues, regardless of your probability. The result of your measurement are discrete; they're not continuous. So based on that, people propose another three postulates. The first is that, okay, to get the eigenvalue, you have to have an operator so that you can have a differential equation to solve the eigenvalue. So the fourth postulate is that for any physics attribute or physics variables, for example, momentum, position, let's say the variable or attribute is expressed by A, this variable in quantum mechanics can be expressed by an operator. Right? And previously we have already seen that the momentum operator is this. Right? This gives you h bar k for plane wave. And now with an operator, you already have an operator. Now you can say that, okay, you can state that the fact that the measurement result in quantum mechanical system can only be eigenvalues. So if you have an operator and then an operator act on an eigenstate, give you an eigenvalue, and then the eigenstate itself, we will later explain more in detail what, the geometrical meaning of this. And then the measurement result can only be A1, A2, all the way down. Okay, it can only be these discrete eigen values. And this is based on experimental observation. Okay.
How would you define eigenvalue?
Yes, we will later talk about this. Okay, so mathematically you can see is that an operator act on a wave function, give you a number times that function itself. Okay, so this is a mathematical definition, and then we'll talk about like in geometry what this really means. Okay, and number 6 is the number 6 is a kind of straightforward, right? We already say that the measurement result can only be eigenvalues. Now, what are the probability of each value showing up in your measurement result, right? So the probability is if you express your wave function as superposition of all these eigenstate, eigenstate of A, okay, eigenstate of A, then the probability of measuring eigenvalue an will be equal to alpha n amplitude square. So the way to understand it, well, not really understand, the way to kind of have an intuitive picture is that think about it as similar to the probability distribution of your position, right? So whatever in the front here represent the weight of this wave function, the weight of of this eigenstate and thus this eigenvalue, right? So because this is a complex number, so if you want to get the probability, you have to have amplitude square, right? So it's kind of similar here, okay? So these 6 combined with Schrodinger equation are the complete, build the complete system for the quantum mechanics we learned in this class. There's, of course, higher level, there's Dirac equation, there's Klein-Golden equation, and then there's other type of interaction that's not, also there's quantum field theory, which are not included in this class, okay? So from postulate 1 to 3, we have kind of covered really in details. Now let's focus on postulate 4 to 6. And you can see here the center of this postulate is really, okay, what is this, right? The eigenstate, eigenvalue, what are they and what do they mean, right? So let me first build a very simple picture. Okay, someone playing guitar? Yeah. Let me first build a very simple picture of this in terms of vector. So eigenstate and eigenvalue, they are not invented in quantum mechanics. They are actually invented in linear algebra, where the wave function are actually eigenvectors. Okay, if you do Wikipedia, you will actually see eigenvector and eigenvalue. And then A is not, well, it's operator, but then it's not the same operator as this. When it was invented, this is actually a matrix in linear algebra. So the way to think about this is that I want you guys to think of this wave function as a vector, like in 3-dimensional space, x, y, z. You can say, oh, how is that? How can you do that? But bear with me here. Think about it. What is a function? Okay, a function is that you have a value at different x, right? So a function can be approximate to a vector with infinite dimension, right? A 3-dimensional vector, let's say v, is a, b, c, right? Probably pointing this way. You can see this is v. So a function can just be understood as an infinite dimension. Infinite dimension, a vector with infinite dimension, because the first dimension can be psi at x1, and then psi at x1 plus delta x. This is your second dimension. And you can keep going, psi x1 plus 2 delta x, and keep going, and to infinity. Right, so your x can extend from minus infinity into infinity, and each of these x, you will have a value. So in principle, this is like you have a space with infinite dimension. Okay, and this is this is actually quite famous. Is that when I think this? Well, I'm not expert on this, but I think this is when people saw the connection between quantum mechanics and matrix linear algebra, then this definition, then people start to work on the infinite dimension of vectors, and this is something called Hilbert space. Okay, so there's a similarity between a function and then a vector. Okay, now let's take a look at what. If you think about the function as a vector, and then for simplicity, we can only imagine things in 3 dimensions. So let's say there's a 3-dimensional vector. Now you have an operator act on the vector. You can imagine the operator. It could be translation, right? Move the vector to other places. It could be rotation along a certain axis. All those are operations. And what the eigenfunction is that under this operation, your vector do not change direction. It only extend, or it only stretch or compress. and stay at the same direction. And if you think about it, this is actually very deep, because what it means is that whatever symmetry this operator has, okay, let me put it in a different way. Your vector is invariant under this operation. Okay, a very simple example would be if your operation is rotation around the z-axis, right? Then you can almost imagine that, okay, your eigenvector must have a vector that pointing to z direction, because no matter how you rotate it, this vector stays the same, right? So this is kind of intuitive understanding of what is eigenvector. Okay, it shows there's more mathematical explanation on this, but what it is that this is a group of special functions that is unique to your operator, and then these functions show some symmetry of your operator. Okay, and when you apply, and in terms of mathematics, it's very kind of straightforward written down here. Your operation act on your eigenfunction, it stay unchanged, right? It only changes the amplitude, it doesn't change the direction. Okay. Any questions here? Yeah. So I guess this is a new concept for most of you. So when you kind of are confused, and then let's say if you're in your homework or in the later lectures, you can always come back to this definition, because like our class, we will not go extra far in terms of mathematics. Okay, we only talk about mathematics if they help our understanding of quantum mechanics. We will not talk about redundant mathematics here. Okay, so so this is a basic framework of quantum mechanics, and then well, there are two alternatives here. One is that I kind of start to give you mathematical derivations of the implication from this of these postulates. The other possible way is that I can show you guys how we can have from postulate 4, 5, and 6, how we can use this to derive postulate 2. Okay, and then I'm not sure which one is better, but we can try to derive postulate 2 first, because it's kind of, well, it's kind of give you an example first, and then go into a little bit more math. Okay. And let me first say, why do we need to derive postulate 2 from postulate 4 to 6? First of all, if you look at it, it's not general enough, right? The only reason we include it here, and all the quantum mechanics textbook included it here, is because it's simple enough that you can understand. But then it's not very general, because it only describes what you will get when you measure position, right? But postulate 4 to 6 actually explain to you, okay, in general, what will happen if you want to measure anything, right? It could be momentum, angular momentum, energy. So naturally, you will see that postulate 2 is actually included in postulate 4 to 6. Okay, so let's jump in here, and then let's, first we can state the question here. The question is, what is the probability based on postulate 4 and 6? Can we know the probability of finding the electron in between A and B, right? Given a wave function. And then because we're not discussing time dependence here, so I dropped the t term here. Okay. So let's see how we can use this postulate. Okay. So first, you have to we have to specify, okay, what we want to measure. We want to measure position, right, where the electron is. So the thing that we want to measure is x from postulate 4. Then we need to know the operator corresponding to position. Okay, the operator. So here it's actually the operator of position and momentum are actually assumptions from quantum mechanics. Okay, the position operator is just x itself. So what it means is that if you have x act on the function f, it will give you the variable x times fx. Right? It just so in this case, the operator x is the same as the variable x. Okay, it's not always the case, but in this case it is. And okay, so that's postulate 4. It's fairly straightforward. Now we need to look at postulate 5 now. Okay, so it says that the measurement result can only be the eigenvalue of this eigenfunction, of this eigenequation. So okay, what is the eigenvalue of operator x? Right? Then what we can do is that we can just use this definition. Okay, let's say we have a wave function which is an eigenstate. Right? Your operator act on an eigenstate. Eigenstate is just a special function. Will give you a number. Let's say eigennumber, eigenvalue. Let's call it x knob. So the notation here is that it's similar to here. The notation here is that x knob is the eigenvalue, okay, and psi x knob is the eigenstate or eigenfunction corresponding to this eigenvalue. Okay, just like psi n is the eigenfunction corresponding to an. And you say, okay, do we know this? Do we know that? No, we know nothing. We just write down this equation and then we'll see, okay, what we know. Now this is a little bit interesting because what you can do is that you can actually write down what the left-hand side is, because we know x, the operator x, is just multiplying x to your function, right? So the left-hand side, we can keep writing. The left-hand side equals to x psi x knob x, right? So we now get an equation, a function equals another function. So if our mathematics is good enough, we should be able to solve it, okay? And since this is actually solved almost 100 years ago, so we'll just go directly and then show you guys the result. And what's interesting here is that if you take a look here, your first reaction when looking at this equation would be no way there's no way that there's a function can satisfy this, because if you take a look, okay, this side is a function, it also has a function, but here x knob is a number, right? Because it's the eigenvalue, it's a number, it's not a variable, it's a number. For example, if I say the eigenvalue is 1, what is corresponding eigenstate? Then you have to put 1 here, okay? But here x is a variable, right? So a number times a function equals the variable times the same function. That doesn't make sense, right? If I choose x not to be 1, the eigenstate to be 1, okay, I measure the electron at position 1, but then your variable can be 2, 3, 4, 5, right? It can be anything. So how can these two equations equal to each other? Okay. So whenever you see something like this, like in your calculation, hopefully you won't see this in your calculation or in any of your research. But anytime you see a left-hand side has no way to equal to the right-hand side, usually that means something is 0 or something is infinity. Okay, and then actually personally I benefit a lot from this kind of experience. Well, kind of this intuition is that when I was doing my physics Olympic game in grade 12, okay, before I apply for college, the last question is something like this: calculating the mass of neutrino. At that time, I didn't know neutrino mass is 0. So at the end, I get an equation that the left-hand side couldn't equal to the right-hand side. And then the question is, what is the mass of neutrino? And then, okay, I say, okay, instead of writing nothing there, I should make a guess, right? So the mass couldn't be infinity, so maybe the mass is 0. And then, and then it's actually correct, and then I got admitted to the university I later went to. Okay, so when you look at this, it's similar. Now, what you can do here is that you can write it down, move this to the right-hand side, then you get 0 equals to x minus x naught per psi x naught x, right? So now it's a little bit clear. Is 0 equals something multiply another thing, right? So this is a function, right? It's a very simple linear function. This is another function, and then the fact that they equal the product equals 0 means that at any given x, at least one of them is 0, right? They could both be 0, but at least one of them is 0. Okay, so we know that at x not equal to x naught, the first term is not 0, right? This is very clear. So what that tells you is that this function, your eigenfunction here, has to equal to 0. Let me the eigenfunction here has to equal to 0 when x not equal to x naught, right? Because x naught equals to x naught, the first term is not 0, the product is 0, so this has to be 0. And then you say, okay, well, we can let the entire function to be 0 everywhere, right? That's obviously satisfy this this equation, but then that would be against postulate 2. Or that would actually not postulate 2, but that would be against well, let's put it this way. This would be against postulate 2, because then if this is 0 everywhere, that means you don't have a probability of finding electron at all. Okay, you can also put this back to postulate 5. You will see, okay, then you won't even have an eigenvalue, because the eigenvalue can be anything if you're always 0, right? So that's just letting this 0 everywhere is a trivial function. So what it means is that when x not equal to, well, so when x equal to x naught, right? When x equal to x naught, the first term is 0. And then to make this function a meaningful function, not a trivial 0 function, so this is not 0 when x equals x naught, right? So this function looks kind of interesting. So for the eigenfunction corresponding to the eigenvalue x naught, your eigenfunction is everywhere 0 instead of at position x naught. Okay, so if it remind you anything, you can think kind of think of here is that this is almost the delta function. Okay, this is almost a delta function now, and and here I want to explain a little bit of our approach is that this is not a mathematical derivation from postulate 4 and 6 all the way to postulate 2. This is not a strictly mathematical derivation. What we show is that in principle, you can from these 3 postulates to arrive here. The benefit of this is that we can skip a lot of mathematical terms, right? There's a lot of definition you need to go through if you want to prove this very rigorously. Okay, so if you see, okay, there's a little bit, you're kind of doing a loop here. That's fine. It's a cost we pay just to just to simplify the math. Okay, so now let's take a look at what this value is when x equals x naught, right? And here, what we use is that if your wave function, if postulate 2 is correct, then your wave function has to be perfectly normalized, right? So the probability of finding an electron in the entire space has to be 1. Right? This is a normalization condition of your wave function. Okay, you have to be able to find your electron somewhere. Okay, so and this is clearly now returned to a delta function now, right? Because what we see is that it's 0 everywhere except at a certain place, and then the integration here is 1. So here you can almost see here is that this is infinity. Okay, so at this point it has to explode to infinity. Otherwise, the integration of a finite number in an arbitrary small interval will not give you a number. Okay, it will give you 0. So, okay, so from here we can kind of get our first solution here is that the eigenstate of position operator corresponding to the eigenvalue x naught is a delta function. And then this delta function is 0 everywhere, but then infinity at x equals x naught, right? And the n here is a normalization factor. And later you will see, well, we actually won't show here in this class, but if you read the textbook or other materials, you see that often people just drop this normalization factor, okay? Because it actually can be normalized. But here, just for to derive this one, we kind of make the math a little bit simpler by adding a normalization factor here. Okay. So any question up to this point? Can you guys follow that how we actually solve this eigenstate for your operator x?
So is this saying that like the wave function is something such that if you just multiply x to it, it becomes a delta function? Or is it saying it's always a delta function?
Itself is a delta function. So the eigenfunction itself is a delta function because it's 0 everywhere, infinity at x equals x naught. Okay, and then your integration goes to 1, so that this has to be a delta function with a normalization factor. Right, this normalization factor is just to make sure that when you do this integration, the result is 1. Well, let's see. I mean, the most important point here is this part. Okay, just to understand that the way we solve this eigenfunction will give you 0 everywhere, infinity at x equals x naught. Okay, as long as you understand this part, okay, how this goes to delta function, there's a little bit mathematical jump. Okay, but then it's understandable because this is how we introduce delta function, right? The reason we introduce delta function is it's 0 as everywhere, but infinity at one spot. Does that answer your question?
I guess I'm just confused because didn't you say that like before the wave function can't be a delta function or something like that?
Yes, the eigenstate or the eigenfunction is a delta function. Yes.
And is that the wave function or?
It's the eigenfunction. It's not the wave function. So the wave function, so think about it in this way, okay? The eigenfunction is a group of unique functions to your operator, right? And then your wave function can be a superposition of all these eigenfunctions, right? So your wave function can be an eigenfunction, but most of the time it's not. It's a superposition of a lot of eigenfunctions. Does that make sense?
Okay, yeah.
Yeah. Okay. Yeah. Yeah, maybe I can give an example here. Is that, for example, okay, let's say this is a wave function, a Gaussian, right? A Gaussian wave function. Okay, so this is a wave function, and then clearly it's not the eigenfunction of x, right? Because we already say that all the eigenfunction of x are delta function, right? So then then how are these two connected to each other? Is that by postulate 3, right? Your Gaussian function, let's say alpha squared, okay, can be expressed as the superposition of all those delta functions. Okay, it could be written down as let's see. So way you can think about it is that, okay, the delta function, let's say delta x minus x naught, only has value at x naught, right? So you can multiply something here. Okay, a function multiply this will represent the value at x naught and 0 everywhere else, right? So this is a function. And then you can move it to the next spot, x1, delta x minus x1. Okay, that's the place next to it. And then you will have another function value here. And then this is a delta function. So you can kind of see where it's going is that, keep going here, is that each delta function represents one spot here. And then whatever, this is no longer a function, whatever number you put in the front can actually mimic your Gaussian function. Okay, so this is kind of the connection between the eigenfunction and generally a function, right? A function can always be decomposed into the sum or superposition of a lot of eigenfunctions. Okay, so we see this in a probably easier example later. Okay, because delta function is always a little bit difficult to understand, and then using as an example is probably not the best example. Okay, so let's see. Okay, so what we have got here is that your eigenfunction now is a delta function. Now we should move to postulate 6, right? Because what we want to do is that postulate 2 says that the probability of finding the electron somewhere is this, right? So if we want to know the probability, then we have to use postulate 6. Okay, so postulate 6 is kind of similar to what I have just shown here, like decompose Gaussian function into a lot of delta function. So the way is that you have a wave function, let's say psi x. Now postulate 6 tells you is that when you express a function as a superposition of the eigenfunctions, then this coefficient will give you the probability of measuring that value, right? If your eigenvalue is an, okay, an, then the probability of measuring an is the coefficient in the front amplitude square, right? So here, because the eigenvalue of x, if it's at x naught, right? X naught meaning that, okay, you measure x and then you get x naught. Okay, that's the meaning of eigenvalue. And for this eigenvalue, your eigenfunction is this delta function. Okay, so if I decompose my wave function in terms of a lot of delta function, and I figure out the coefficient in the front, then I will be able to know what is the probability of measuring an electron at x naught. Right, so this is the logic. Okay, simply directly applying postulate 6. Okay, and because it tells us the probability, this also tells us the probability. If our math is good enough, we should be able to go from postulate 6 to postulate 2. Okay, so there's some math details here, but I'll just show you a general idea of how to do this, and then the math detail is not really that important. And let's see, yeah, and then we are a little slow on time, so I will skip a few of them. So in general, what you can do is that you can write down your wave function psi x, just use postulate 6, right, as a superposition of your eigenstate, right? Your eigenstate psi x naught. That's your eigenstate by definition. And there's a coefficient in the front. Okay, let's call it alpha x naught. Right, there's a coefficient in the front. And then I sum all the x naught from minus infinity to infinity. Right, so what this means is that I express my wave function as a superposition of all the eigenstates of the position operator. Right, so later when I do measurement, this is my probability. Right, if I can do this decomposition, then this thing amplitude square will give me the probability of measuring the electron at position x naught. Okay. So you'll say, okay, how do we do this? The way to do this is that use this delta function, and then so let me see how we can show this clearly. Okay, let's see if I'm interested in alpha x1, right? Let's say position x1, I'm interested in the amplitude alpha x1. This will later give me the probability. One thing I can do is that if I want to get this, I can multiply psi x1 x, okay, psi x, and then do an integration from minus infinity to infinity. Later you will know this is called orthogonal condition. Okay, we'll also talk about that in detail. And the right hand side, what it will happen is that you will see the right hand side is sum, okay, alpha integration multiply psi x1, and then this side is psi x knob. Okay, minus infinity to infinity. Okay, and you can see here, you can already see here what will happen. What will happen is that we know x knob, psi x knob is 0 at everywhere other than x equals x knob, right? Psi x1 is also 0 everywhere other than x equals x1, right? So if one of them is 0, then the entire thing is 0. So the only possible way to make this non-zero is it will be non-zero when x1 equals x knob. Or I should put it x knob okay. You sum x knob from minus infinity to infinity. It looks scary, there's a lot of terms, but those terms are useless unless your x knob is equal to x1. Otherwise, one of these functions will be 0, right? So if you have that in mind, then this will simplify to alpha x1 sum infinity psi x1 x psi x1 x dx. Right, and this is something you can calculate because you already know the waveform of your eigenfunction. Okay, so the right hand side is kind of interesting. You actually get this plus integral. You just need to do that. And then the left hand side, you can use the same argument here now. The left hand side is a delta function. Right, so the left hand side is n psi x1 x is a delta function. Right, you just replace x knob with x1, and that's your eigenfunction, and then psi x dx. And then here we know that anything integrated with the delta function, simply the result simply give you psi x1, right? Because it's 0 everywhere, infinity at x1, x equal x1. So it's kind of like a sampling, a point that pick your function at x1 point, right? So what this turns out would be if you finish all the calculation, and then I would skip a few steps here, but then what you eventually get, you will get alpha x1 equal to the normalization factor here n, and then psi x1. So it's kind of very interesting is that the probability, the factor that gives you the probability is just a constant times your wave function at this point, psi x1, right? So this is true for every x1, and of course this is true for every x0, right? So then this you can write it down as There's a normalization factor here, x knob, again, minus infinity to infinity. And then this coefficient now is psi x1. Sorry, I think it's x1. No. Yeah, this one. Psi x1 is your wave function value at x1 times your x naught, because here we're summing x naught. Okay, so let me repeat what this is. So what this is that your wave function can be write down according to, because you want to use postulate 6, so according to postulate 3, your wave function can be write down as a superposition of all the eigenfunctions of position operator x, right? And each of these position operator, each of this eigenfunction, what it means is that if you measure this one, it will give you position x naught, okay? Because your measurement result is a corresponding eigenvalue, okay? Now, when you write it down as this, and then by using the delta function, okay, we kind of get that, okay, the coefficient in the front that according to postulate 6 will give you the probability is actually just the wave function itself, the value of wave function at this position times a constant, okay, times a constant. Now, what this tells you is that the probability of measuring x equals x naught, okay, there's a normalization thing here, is proportional to right, according to postulate 6. This coefficient here is your probability. Okay, so this is actually the same as postulate 2, and then the difference is the normalization factor. And you can go back into the note. There is some math detail there. I'm not going to spend my time here, but there's math detail there to show you that, okay, the coefficient is actually, when you convert this into probability density, you actually get exactly postulate 2. Okay, so this idea here is not, well, let me put it this way, it's not to scare you with the math, but it's to show you that, okay, this is actually a basic way of solving a quantum mechanical problem. Let's say when you try to measure a physics attribute, right? What you do is that you first, okay, have a physics attribute, you write down what is its operator. Then you solve its eigenstate, okay, eigenstates and eigenvalue, and then you express your wave function, which is solved from Schrodinger equation, right? Schrodinger equation determines the evolution of your state, okay? You decompose that into the superposition of all your eigenstate, and this coefficient in the front will give you the probability of your measurement result. Okay, so this is one example of the natural flow of how to solve quantum mechanical system, and then we'll have a much better example later, okay, in probably starting next week. Any questions here? Okay. So let me say this part, even if you don't understand, that's perfectly fine. It will not show up in homework or exam, but I think it's kind of something that you have to know, that the postulate 2 that we talk so much about so many times is actually not a real postulate. It's a derivation from other postulates. Any question before we move forward? Okay. So the following, there are about 20 minutes left here, and then the next class will be a little bit mathematical in terms of not numbers, but just symbols and calculations. And the point here is to tell you some basic fact about eigenstate, eigenvalue. Okay, because these are critical, like at the center of quantum mechanics, and then it's actually a little bit beneficial to work on the math a little bit first before we go into further detail. So this is, it's interesting is that the when we do a research work and then the communication office try to write a news on things we do, there's always a difficulty is that how to make other people understand what we do. And then for physics-oriented thing or a little bit of engineering-oriented thing, you will find it extremely difficult to talk about the subject if you don't know the math. Okay, so for every different subject, if you think about it a little bit, like classical mechanics, if you really want to solve it, you actually need calculus. And then for statistical physics, there's other things you need. And then for the EM field, you need to solve differential equations. And for quantum mechanics, you kind of have to know eigenstate and eigenvalue. Okay, so for every math, there's some special mathematics. For every physics subject, there are some mathematics there. And actually, in the early age of science development, a lot of the math are coming from the physics. But nowadays are very different now. Okay, so there are three important things we need to know about eigenstate and eigenvalue. Think about it in, this is a math thing, okay? So the first is that for an operator, there are many different eigenstates. Okay, there are just many. Just like, when you solve the mechanical wave function of the string, right? You have the frequency. There's an integer there. You can let n equals 1, 2, 3, 4, 5 all the way to infinity. So for most of the operators, when you solve the eigenstate and eigenvalues, there are infinite amount of them. Okay, there's some special case that's not infinite, for example, spin. And then the second thing is that for the eigenfunction, they are actually orthonormal to each other. Okay, they're actually orthonormal to each other. And this is actually why you can decompose them into like this. Decompose a function into the superposition of eigenfunctions. Because if they're not orthonormal, then you actually have overlapping terms. Okay, and we'll spend about 10 minutes to explain what does orthonormal mean here. And then the third, as kind of a derivative of all this, is that the operator A has to be Hermitian, which we will talk about this in the next class. Hermitian for any measurable physics quantities. Okay, so now let's start with the definition of orthonormal. Okay, this is extremely important because, like a lot of the problems in homework and exams, if you don't use orthonormal of the eigenstates, then you will actually really spend a lot of time, okay, instead of having a direct answer. Okay, so first, what is orthonormal? we can again think about it in a vector term, right? In a vector, let's say two-dimensional space, I have vector v, and then when I say v is orthonormal, in another way is, let's say v is perpendicular. Orthogonal and perpendicular are actually the same thing if you learn linear algebra. So if we say U is orthonormal or perpendicular with V, what we mean is that, okay, they're 90 degrees off each other, right? And then if you write this down in terms of vectors, for example, three-dimensional, then V, let's say, is x1, y1, say x1, x2, so just y, x1, y1, z1, right? That's the first vector. And then the second vector is x2, y2, z2, right? So to see if these two vectors in general are orthonormal or are perpendicular to each other, what you can do is that you can do an inner product of these two, right? Or dot product. Inner product or dot product. The geometry, well, the mathematical meaning is of dot product is that you project one vector to the direction of another vector and see how much they overlap, right? If they don't overlap, if the overlap is 0, that means they're perpendicular to each other. So in a vector, okay, then this will give you, okay, I hope you guys have learned this before, x1, x2. The inner product is just x term times x term, y term times y term, z term times z term, right? And then you multiply them, you add them together. x1, x2 plus y1, y2 plus z1, z2. Okay, so this is the definition of orthogonal or perpendicular in vector. Now we can extend this definition into wave function. Okay, wave function, again, as I said, wave function, you can think of it as a vector with infinite dimension, right? So for each dimension, it could be per psi n x1, right, is its value. Per psi n x1 plus delta x is the next element, and keep going, right? So this is a function is just a vector with infinite dimension, right? So now, how do you define the inner product of two functions? If they're real, right? If they're real, let's start with real case, because the wave function can be complex, and that one will just tell you the answer. But for a wave function, if we have two wave function, and if we think about them as vectors, infinite vectors, vectors with infinite dimension, then let's say we hold the same definition of inner product to them, then what you will see is that, okay, then what we should do is that we should multiply the same term or same dimension here, okay, from the first function and the second function, and then we add all of them together, right? So instead of x1, x2, z, and then you have to add all the other terms together. So the inner product for a function, just directly from, for a real function, okay, directly extended from vector space, vector result, is sum, okay, psi n x times psi m x, x equals from minus infinity to infinity. Right, just dot these all terms together and then you sum them. Okay, and then you can see that, okay, this is, let's say, proportionate. Okay, and you can see that the sum is just, the other way to write the sum is just integration. Right, so this is the same as minus infinity to plus infinity, your function, the other function, dx. Right, when you sum all this together, if the change of x is infinitely small, then you can change this to the integration. Okay, now this is for the real function, a function with a real value. If it's imaginary, if the value could be imaginary, then this one you just add the complex conjugate to one of them. Okay, you just add the complex conjugate to one of them, and that's the inner product. Okay, and the reason for doing this is that it's very simple. Is that if you inner product a vector, a function with itself, it has to be 1, or it has to be a real number, right? Because you project something onto itself, and it has to match perfectly. And then if you see that, if you try to do that with complex number, then what it means is that we do psi n with psi n. If you wanted to always return to a real number, then the best way is just to do psi n amplitude square. Okay, so that's why there's a conjugate here. Okay, so so here, what we let me try to summarize what we got here is that by comparing our result by comparing with the vector, okay, how orthogonal or how perpendicular is defined in vector, okay, we know that the inner product of two functions is now defined as the integration of this function conjugate times this. Okay, the product of these two, one of them is a conjugate, and then do the integration. And then the meaning of they two are orthogonal or perpendicular, two functions are orthogonal, perpendicular to each other, is that the inner product equals to 0. Right? It's the same as in your vector, right? If two of them are 0, if two vectors are perpendicular to each other, then their inner product, their dot product, is 0. Okay. Any question on this part? Now, we have 5 minutes left. Let me quickly show you guys that why orthogonal or orthonormal is important in quantum mechanics. It's because all this, we can quickly prove that all these eigenfunctions if they belong to the same operator, okay, they're actually orthonormal to each other. Orthonormal normal means that if it's orthonormal, then so the inner product, of a function of itself is always 1. Okay, it's like perfectly normalized. This is what we need for quantum mechanics, right? Because they represent probability of finding this, finding a function in finding the inner product of this represent the probability of finding the electron in the entire space, and that has to be 1. Okay, so that's why all the functions in quantum mechanics has to be normalized. Now let's quickly prove this. Oh, actually we can't until we show that A is Hermitian to each other. Yeah. Okay, then let's do the Hermitian first. Let me do the Hermitian very quick here. So if you find this a little bit difficult to understand, that's perfectly fine, because they're kind of mathematical, and then it's all new, and then there's a learning curve here, and it's perfectly normal. So when we look at this, and then we say that when you measure a physics attribute A, the measurement result can only be AN. And what that tells us is that AN is a real number, right? Because when you measure something, it can be imaginary. Your voltage is always real. It could be positive, negative, but it's a real number. So AN is real, always real. Okay, always real. But not, so that actually limits our choice of the operator, because the operator, the eigenvalue of an operator doesn't necessarily have to be real. Okay, it could be imaginary. So what we can have here is that if all of them are real, okay, one thing you can derive is that all the operators are Hermitian operator. And let me write down the definition of Hermitian operator. The definition of Hermitian operator is that the inner product of A. You know what? Let's leave it to next class. I don't want to rush this part. We have only 1 minute left, and then there's about 20 lines of math, and I don't think it's a good idea to rush it. Okay. So coming back, so next week when coming back, we will show you guys that the operator for all the measurable physics variables has to be Hermitian. Okay, and what it means for Hermitian, and then from Hermitian we show you that. Okay, all those eigen states are orthogonal to each other, and then how that can help us to solve a quantum mechanical problem. Okay, and I kind of want to apologize that unfortunately this is a little bit mathematical, but then there's no way to avoid this, because if we skip all this, and then then you kind of can't work on any real quantum mechanical problem. So probably spend a little bit more time when the homework of this section is released, and then try to figure out how what this really means. Okay.